So in this video, we will be discussing physics of Savart's law. What is Savart's law? Basically, if there is a wire which is carrying current, and there will be certain magnetic field due to it. So for example, we have this particular diagram. So in this diagram, there is a charge Q which is located over here. I don't know if my spotlight is working on. Yeah, it's working. Okay. So here is the charge Q with off, and there is a wire, and the wire which is carrying the current here, and it is carrying the current element DL. Whose length is DL. So say for example, this is the wire which is carrying the current, and its current element, its length is DL, and there is a charge Q. And from this current element to this point P, there's some distance, and that distance can be denoted by R. So now we are interested to know what is the magnetic field at this point P. What is the magnetic field at this point P over here? So that is what we are interested to know. So that is why I will be, I'll be writing the equation for that. Now, what is the usability of this equation? Like, why is it necessary to know the Savart's law? Why are we interested to derive this equation? Well, on a detailed note, it is always important to know that what is the magnetic field generated by a wire which is carrying current, and then later on in detail there will be there will be different generalization and everything which might give us the idea about new advanced technologies. Say for example, waveguides. If you want to understand everything about waveguides, then the basics of this Savart's law and magnetic field due to a current, and all these details might help us to understand some advanced applications in physics and in electronics and communication. So yeah, so I'll be just doing a short derivation of how do we get the Savart's law, and my future videos will also involve the generalized equations, like different cases which involves a current carrying wire, and in current carrying wire in different ways, like with different cases. So I'll be writing. So we are interested to know what is the magnetic field at this particular point, that is at point P. We want to know what is the magnetic field at point P. So that's why I will be writing that the magnetic field at a point P, okay, due to current element. So you clearly know that what is the current element over here. So a current element over here is clearly this one. This DL stands for the current element here. Okay, so from this current element to this point P, what is the magnetic field? So that can be given as dB. B is the magnetic field is a vector quantity, and is equals to 1 upon 4 pi epsilon 0 c square. Some of the thinkers might question that why there is presence of epsilon 0 c square. So in future, I might try making video on the same, and if I'll be making the video on the same, then I'll be surely putting it in the description box below so that you can find out that what is the significance of epsilon 0 c square over here, and why are we using it in these equations involving the magnetic field and electric field, etc. So this is given as I into dl cross r dl cross r upon r cube. Well, where is this formula coming from? We will also try to know the details of it. So let me explain you each and every term here. Now c is the speed of light, then I is the current element, it is the current, sorry. DL is the length vector, dl is the length vector of the current element, like whatsoever current element we have taken here, like the one which you can see with the red patch. So that particular current element, it has a certain length, and then r is the vector. So you clearly can see from the diagram here. So r is the vector, and that vector, it is joining the current element and point p. So yeah, then then there is 1 upon epsilon 0 c square. So we can replace this epsilon 0 c square as mu 0, and it is actually the permeability of vacuum. So we can write it as mu 0 upon 4 pi into I dl cross r. So this can be written upon r cube. We can get this. So this is the mathematical form of Bio-Savart's law. But now we can, further write it in terms of the magnitude. So if we want to write the magnitude of the Bio-Savart's law, well, you should know that what is this particular equation that we wrote about over here, this one. So this is actually the mathematical form of Bio-Savart's law. But then I am writing it in terms of the magnitude. So that is going to be dB is equals to mu 0 upon 4 pi into IDLR sine theta on R cube. So then, the R and R square, R and R cube, they get cancelled. And so that's why we get dB is equals to mu 0 upon 4 pi into IDL sine theta upon r square. So this is what we get. So here theta, what is theta? So theta is the angle between between the dl, that is the length element, and the vector r. So basically, if you see this diagram, so this is before that, let me write down. So this is the magnitude of the magnetic field. Magnitude of the magnetic field. So you must be wondering that what if we want to get D from dB? So for getting that, we need to do the integration. So integration and further, work can be done, and then we can get the complete pure expression for B. But that can be manifested in several numericals that we do. So let us physically imagine that what is this diagram about. So you consider that this particular screen is a plane, okay, and the direction of the field is perpendicular to the plane containing the current element. So the magnetic field, okay, it is perpendicular to the plane. So imagine me, putting my stylus pen on the screen, okay, in a horizontal manner. Sorry, in the vertical manner. So that is how the magnetic field is going in, and the point P, the and there's a point P here. Okay, so now you imagine that on this particular current element here, okay, on this particular current element, you put your right palm. Imagine putting your right palm and then curl your fingers. So, the the thumb will be upwards, right? So the direction of thumb will basically give you dl cross r. Okay, the the fingers will curl towards r vector, and dl will be along the palm, right? So this way the magnetic field is perpendicular to the plane. So either it is going in or coming out of the plane. So I hope you are able to imagine this. Once again, and there's a point P, and then there is this current element over here. So you try to put your right palm over there, and you try to curl your fingers. So when you curl your fingers, that will be the direction of R, and there will be a thumb which will be pointing upwards towards your face. If you have the laptop screen or phone screen on the table surface or on the placed on the land or on the table surface. So whatever your thumb, wherever your thumb is pointing, okay, in pointing in the upward direction, so that would be the direction of the field. Okay, so basically this equation that we found out, like this equation that we have derived, this equation dB is basically pointed in the upward direction provided there is the phone surface or the plane surface staying on your table, either upwards or it is pointing downwards. So either the field, the magnetic field is either coming out of the plane or it is going inside the plane. So I hope this explanation is helping you to imagine that what will be the magnetic field like around the current carrying conductor. So see you in the next video. Bye.